All right, folks, what we're going to talk about in this particular lesson is called polar functions, okay? Now, it is what you think if what you're thinking is going back to polar coordinates. And what we're going to do is we're going to take what we understand about polar coordinates, and then we're going to take what we understand about functions, and we're going to put them together. So let's see how these two work together. What we understand about polar functions, there are a couple things. The first one is that every point on the coordinate plane can be represented using polar coordinates, where we do the radius, that's the distance from the center, the origin, 0, 0, based on an elevation, some kind of angle measure, right? And then what we understand that the relationship between the radius and theta with respect to the rectangular coordinates x and y is that x is equal to r times cosine of theta and y is equal to r times sine of theta. So this was our conversion. These were our conversion formulas between the xy coordinates and the r theta coordinates. And hopefully you did plenty of examples of converting between the rectangular coordinates and the polar coordinates, okay? So that is polar. Now what we had learned, and we're now going to actually change this, is that when we were doing polar coordinates, we said that theta would always fall between 0 and 2 pi, right? That theta is only going to take on a value between 0 and 2 pi. Okay, that's going to change now. Starting with polar functions, we can actually have theta go on to infinity in a positive direction, and we can also have theta go to negative infinity. All right, now let's talk about functions. What do we understand about functions? Well, we know that functions, very simply can be something like y is equal to x squared minus 3x plus 4, right? We've also learned about rational functions this semester, which would be like y equals x minus 5 over 2x plus 1, okay? And other kinds of very interesting stuff. Here's a rational function, here's a quadratic function. We also have linear functions, which take on mx plus b, like negative 5x plus 4. We just learned about trigonometric functions like, 7 cosine of 5x minus 2. So there's all different kinds of functions. And in every single situation with functions, we have two variables. We have a y variable and we have an x variable, right? X is the input variable and y is the output variable. And what we're saying here is that you give me any x and I will then give you the y that goes along with that function. Then we also know that if there is a function between x and y, that what that means is there are an infinite number of possible points, right? An infinite number of solutions. If x is this, then y is that. If x is this, then y is that. And so if you change the x value, you wind up in most cases getting a different y value. So you have an infinite number of x comma y solutions, right? X, y points. And that usually results in having a graph, a curve, okay? A graph or curve which can be plotted on a coordinate plane, and that graph or curve represents all of the infinite number of solutions that match whichever function you're dealing with, okay? And so we know the cosine, looks like this, okay? We know that linear functions, this negative 5, that would be a downward sloping straight line. We know that there would be a vertical asymptote on this one, and that it would probably do something like that, right? Quadratics usually have the shape of a parabola. If they're positive, they go up. If they're negative, they go down. So we know that each function has a unique graph that represents an infinite number of solutions between the x and y coordinates, okay? All right, so we're going to take that same idea, but instead of doing x and y, we're going to do r and theta, okay? R and theta. And the idea here is this, is that we have a relationship between r and theta, where you give me a theta, that's the input, and I'll give you an r. And so what we say is this, is that when we write it as a function, we say r is a function of theta, okay? And then over here, we'll have some expression that includes at least one theta. So for example, we can have r is equal to, 3 theta plus 7, okay? 3 theta plus 7. Now, in x and y, in y and x, this would be linear, but this is not linear. Okay, in fact, I'm going to show you in just a little bit. We're going to go on Desmos, and you're going to see that these polar functions, when they create a graph, it's weird looking, very weird looking, but also very neat looking, creating very pretty patterns. And you'll find that you can actually have a lot of fun trying to create pretty drawings or patterns using polar functions. And you can accomplish a lot of things with polar functions when you graph them than you can when you're trying to graph with x and y in rectangular coordinates. Okay? So let's say that we have this polar function, r of theta is equal to 3 theta plus 7. Well, what we can now do is we can create, just like we do in x and y, is we can create a theta radius, an angle measure and radius t-chart, right? So let's say we can plug in 0, 1, 2, 3. Now understand that these are radians, right? Our theta angle measure, this is radians. So you could put them in as whole numbers, but you can also enter them as, let's say, 0, pi over 6, pi over 4, pi over 3, etc., etc. Okay? So let's say we did put them in as 0, pi over 6, pi over 4, and pi over 3. What we would then do is we would just simply plug these thetas in here for theta, and we would calculate the expression to get the radius, okay? So if we put a 0 in, 3 times 0 is 0, plus 7 is 7. So when the theta angle is 0, the radius is 7. When the theta angle is pi over 6, well, 3 times pi over 6 is equal to 3 pi over 6, which is actually pi over 2, plus 7, okay? So we would have pi over 2 plus 7 would be our radius. Now, pi over 2 is about 1.57, so it's approximately 1.57. So our radius in this case, if you add 7 to this, would be approximately equal to 8.57, okay? And we could do the same thing, plug in pi over 4, plug in pi over 3, okay? One of the things that I want you to be able to do is this, is with a calculator, I want you to be able to produce a table given a particular polar function. And that's what I want to do right now. To get you started, is I want to get you ready and just teach you the skill of being able to use a calculator to identify, to create a t-table using a polar function. Okay, so let's say that we have this kind of simple polar function. We have r is equal to 2 theta minus 5. Okay? All right, so what we're going to do is we are going to create a t-table, okay? And we're going to have our theta inputs right here, theta, and that will give us our r outputs, right? Now, let's go ahead and do it. I'd like to do it in radians if we can, because it's easier to plot when it's in radians. So we'll do our radians starting at 0, and then we'll do pi over 6, then we'll do our usual pi over 4, then our pi over 3, then our pi over 2, and let's stop there. Okay, so 0, pi over 6, pi over 4, pi over 3, and pi over 2. So we're just going to do 5. So we're going to plug them in. We're going to put a 0 in here, and 2 times 0 is 0, and 0 minus 5 is negative 5. And do you remember me telling you that, previously we said that radiuses have to be positive, right? Well, now is a great way to introduce the idea that radiuses can actually be negative, and what that means is when they're negative, that means that they're going to go in the opposite direction than they would have been plotted. Now, in this particular case, if we were on a polar graph, right, with the circles, okay, So let's say we have 1, 2, 3, 4, 5. Okay? All right. So normally with a 0, that means that we're pointing in this direction. We're right along the x-axis because a 0-degree angle means we're on the initial side. And so if this said 5, then what we would do is we would go out 1, 2, 3, 4, 5, and we would plot a point right here. Except this isn't 5, this is -5. And so what that's telling you to do is go in the opposite direction. Instead of going to the right, we're going to go to the left, and we're going to go 1, 2, 3, 4, 5, and we would plot a point right there. Okay, that's what a negative radius means. It means linearly go in the opposite direction that distance. Okay? All right, so now we're going to plot pi over 6. If we put a pi over 6 here, 2 times pi over 6 is pi over 3. Because 2 times pi over 6, 2 over 6 is 3, so this is the same thing as pi over 3 minus 5. So in a calculator, I'm going to do pi divided by 3, so pi over 3. And I can even key in 2 pi over 6. It'll still give me the same thing, which is about 1.0471997. Then I'm going to subtract 5, and I'm going to round, let's say, to 3 decimal places. So this is going to become negative 3.953. Negative 3.953. Now let's try pi over 4. So 2 times pi over 4 is the same thing as pi over 2. All right, and then we're going to subtract 5, and we get negative 3.429. Then we're going to do pi over 3. So 2 times pi over 3 minus 5 gives us negative 2.906. Negative 2.906. And now we're going to put in pi over 2. 2 times pi over 2 is the same thing as pi minus 5 gives us negative 1.858. 858. Okay? And that's all I want you to do for now. We're not going to plot them just yet. I'm going to show you what it looks like when we do plot them. But for now, this is all I want you to be able to do. Okay? Let's do another example. All right? So here's another one. This one's a little crazy looking. It looks like a quadratic, doesn't it? But instead of y equals x squared minus 2x plus 3, we have r equals theta squared minus 2 theta plus 3. And here's what I'm trying to show you is that you can make these things look like whatever you want to make them look like. Okay? But this form in polar coordinates will not result in a parabola. Well, not this one anyway. In fact, I'm going to show you later in one of the later segments how you accomplish a parabola using polar coordinates, and it doesn't look like this. But all I want you to do here is I just want you to create a table, and I want you to do your 0, your pi over 6, your pi over 4, your pi over 3, and your pi over 2. Okay? All right? And so this is our theta angle and then our radius. If we had a theta angle of 0, we'd put a 0 in here. 0 squared is 0, minus 2 times 0 is 0, plus 3, so we'd come up with a radius of 3. Now, if we put pi over 6 in here, we'd have to do pi over 6 squared minus 2 pi plus 3. You're probably better off just keying it all in the calculator. So I'm going to do a parenthesis, then a pi over 6. I'm going to close the parenthesis, then I'm going to square it. Squared minus 2 times, I'm going to put it in parentheses again, pi over 6, close the parenthesis, then plus 3, and I get 2.227. 2.227 is my radius. Okay. Now I'm going to do the exact same thing with pi over 4. Now in my calculator, I can actually just push the up arrow and go through and just change all the 6's to 4's, and it'll give me the correct answer. So now I have pi over 4 squared minus 2 times pi over 4 plus 3 gives me 2.046. This is interesting. So you can use these a numerical table to get an idea of what's happening in the behavior of the polar function. Look what's happening here. My values are decreasing. I'm going from 3 down to 2.2 down to 2, right? And so I get the idea as my theta angle increases, I have a negative slope here, right? My values are decreasing, okay? Well, let's see what happens at pi over 3. Let's change those 4's to 3. So I got pi over 3 squared minus 2 times pi over 3 plus 3. And it's going down again, but this time it's 2.002. All right? You know, this almost looks like an asymptote, like I'm going from 3 down to 2. See, this is closer to 2, closer to 2, closer to 2. Let's see what happens at pi over 2. Let's change the 3's to 2. So I got pi over 2 squared minus 2 times pi over 2 plus 3. Oh, something interesting is happening here. Now I've got 2.326. Now I've gone up. All right, so that's it for this particular equation. Let's just try one more with something a little crazy. All right, so here's one. It's a little crazy here. Let's say that r is equal to 2 to the power of theta. Let me grab my calculator. I left it over here. And then here's our t-chart. So all we're going to do is we're going to identify the radius based on the 5 theta angle measures, 0 up to pi over 2. So we're going to do 2. We're going to plug in 0 for theta, 2 to the 0 power. We already know what 2 to the 0 power is. That's 1, right? Okay. Now let's do 2 to the power of pi over 6. So 2 to the power of, now I'm going to put pi over 6 in parentheses because this is a scientific calculator. And if I key in 2 to the power of pi over 6, what it's going to do is it's going to do 2 to the power of pi, and then it's going to divide that value by 6. So I got to put pi over 6 in parentheses so that it does 2 to the power of pi over 6. So be very careful about that when using a scientific calculator. So 2 to the power of pi over 6 gives me 1.438. Okay, I hope you're doing this with me. Don't just watch it. You should have a calculator in front of you doing the example with me. All right, now I'm going to do 2 to the power of pi over 4. Well, with this calculator, I can just hit the up arrow, go over and change the 6 to a 4. And now I have 2 to the power of pi over 4 is 1.724. 1.724. See, also doing this along with me right now, you can see how I'm rounding. And so if you struggle with rounding, you can see how I expect you to round when you're doing the problems in the quizzes. All right, so now we'll do 2 to the power of pi over 3. Pi over 3 gives me 2.067. 2.067. And now 2 to the power of pi over 2 is going to give me 2.971. 2.971. Okay? All right, we're going to do just one more example, and with that particular example, we're then going to actually plot the points. We're going to plot all the points r1, comma, theta, 0. So like this would be the point 1, 0 on a polar coordinate plane, 1.438, comma, pi over 6. Only I'm going to make it a little easier. I'm going to use numbers that make it a little easier to graph, okay? Okay, so because I want to graph this one, I'm going to put the graph right here. I'm going to project the polar plane up here, and I've put our t-chart over here, and I want to do a bunch more coordinates, okay? I actually want to start at 0, and I want to also do over 12s. So I want to do pi over 12, then I want to do 2 pi over 12, which would be pi over 6, then pi over 4, then pi over 3, then, let's see, that would be, 12, 2, 3, 4, then 5 pi over 12, then pi over 2, then 7 pi over 12, then 2 pi over 3, then 3 pi over 4, then 5 pi over 6, 11 pi over 12, and then pi, okay? So here's what I would do is why don't you go ahead and take a few minutes, pause the video, plug all of these values into this polar function, which is, that's not 60, that's 6 times theta over pi plus 1. Now, I'm going to give you an example. I'm going to do this one together. Let's do pi over 4 together so that you can get an idea of how this is going to work. So I'm going to do 6 times pi over 4 over pi plus 1. Now, you may say, hey, this looks really crazy. Well, here's what's going to happen. In every one of these cases, this over pi, that is going to cancel the pi. So that now what we really have is 6 times 1/4 plus 1, okay? So like this one would be 6 times 7/12 plus 1, all right? So you're really just canceling out the pi. 6 times 1/4 is 6/4 plus 1. 6/4 is the same thing as 1.5. So this is 1.5 plus 1, so this equals to 2.5. And so right here, the radius is going to be 2.5. And so what I'd like you to do is, I would like for you to start here and fill in the table. And what I'll do is, I'm going to break the video, and when I come back, it's all going to be filled in. All right, so hopefully this is what you got for the radii. Hopefully you eventually caught on to the pattern that it's basically just going up by 0.5. So we got 0 and 1, pi over 12, 1.5, pi over 6, 2, etc., all the way around to pi. All right, so what I'm going to do now is I'm going to go ahead and project a polar plane up onto the screen. Here we go. Make sure that we got that set up and ready to go. There we go. We got a polar plane. And now what we're going to do is we are going to plot all of those points right there. So we're going to plot the point 0, radius of 1. So a zero angle measure, 0 theta, means that we're running along the initial side, which is right here. Okay? And so the radius is 1. So we're going to go to a radius of 1, and here's the circle that has a radius of 1. This is 1, 2, 3, 4, 5, 6, 7. Good news, our largest radius is 7. Okay? So we're going to go to 0, 1, and we're going to start right here. That is our starting point. And that's one of the interesting things about a polar graph, is that it can have a starting point if you set an interval for the theta. And in this particular case, our interval for theta is going to be from 0 up to pi. Okay? Now, if we let it go all the way back to negative infinity, then it's just going to keep, it's going to do whatever it does all the way back to negative infinity, which could become a swirly all over the place. Okay? But usually we set an interval for our theta value. We're starting at 0 and we're going up to pi. Okay? So we got 0, 1. Then we have pi over 12. Here is the terminal side for pi over 12. And we're going to go to a radius of 1.5. Well, here's a radius of 1 and here's a radius of 2. So we'll go about halfway between. So that's about 1.5 right there. Okay? Now we're going to go to pi over 6 and 2. Here is, oh, that's pi over 6. Supposed to go to pi over 12. Sorry. There's pi over 12. And 1/2. Now we're going to go to pi over 6 and 2. Okay? Then we're going to go to pi over 4 and 2.5. Here's pi over 4. We're going to go to 1, 2, 2.5. Now look at this. Isn't that interesting? See, we've got sort of a curving line here. It's sort of curving up. All right? It's not a straight line. Then we're going to go to pi over 3 and 3. So here's pi over 3 and 1, 2, 3. Okay, here's 5 pi over 12, which is at 3.5. So that's 1, 2, 3.5 right here. All right. Then we're going to go to pi over 2 and 4. Here's pi over 2, 1, 2, 3, 4. So put a dot right there. And now we'll do 7 pi over 12 and 4.5. 1, 2, 3, 4, 4.5. And then 2 pi over 3 and 5. 1, 2, 3, 4, 5. 3 pi over 4 and 5.5, 1, 2, 3, 4, 5.5. 5 pi over 6 and 6, 1, 2, 3, 4, 5, 6. 11 pi over 12 and 6.5, 1, 2, 3, 4, 5, 6.5. And then we have pi, which is over here, and 7. And look at this. Isn't this weird looking? Look at that. Look at all these dots. And what we would now do is we would now connect all of these dots with a curving line. See if I can do this without messing it up too bad. I am not an artist, but I have done this a few times. And look what we have. We have this weird looking curve. Okay? And what I can tell you is that the shape that you would get if you kept going, if you continued, you would have something that looks very similar to a nautilus. You know, like the creature, the nautilus, that does, where its shell does something like that. That's exactly what's happening here. It's starting kind of in the middle here, and it's curving out, and then it would get larger and larger. The radius would get larger and larger and larger and keep curving out as the angle measures go around and around and around, okay? All right, so what I'd like to do now is I'd like to show you how to play around with Desmos as we look at the graphs of different kinds of polar functions. And I want to give you a chance that you may be interested in going on to Desmos yourself and just playing around to see what kind of shapes you can create. Okay, here we are. I've opened up a Google browser, and I'm going to go to www.desmos.com, press enter, and then I'm going to go to Graphing Calculator right here. And what I usually do when I first come in is I go over here to Graph Settings, and I turn off minor grid lines, and then I set the steps to 1 each. So the X steps are at 1 and the Y steps are at 1. That way I can see the numbers on the grid, or I can see them as 1 by 1 squares. All right, so now what we're going to do is let's go ahead and graph what we just looked at up on the board. We're going to put R is equal to, and we want to do 6 theta over pi, right? So here's what I need to show you. So let's do 6 over, well, hang on a second here. I want to show you how to do theta. If we do, to get a theta, the Greek letter theta, you have to type out the word theta, T-H-E-T-A, and then all of a sudden it turns into the symbol theta. Now look at this. Isn't this neat? This creates a sort of spiral, and that's oftentimes what you see in a lot of polar graphs is you'll see interesting spirals or other weird kinds of shapes. And that's what we're going to look at right now is we're going to look at some of the weird shapes that you can see with polar graphs. Let's see here. We're going to turn this into 6 theta over pi. So I type in pi and I get pi plus 1. And then also remember, see, look at what you're seeing here is the interval. We started at 0, right? And we went up to pi. So I'm going to type in pi. And so look, it only has a piece of the graph. It stops the spiral right here. Just like where we plotted, we started plotting here. Then we plotted out here, then here, then here, then here. And it gave us this interesting, weird-looking curve, right? So this is a polar graph. And if we extended it, let's say we went out to 2 pi. So I'm going to put a 2 pi on here. This is what it would do. You can see that it would go all the way back to the x-axis, and this is what we call a nautilus. Okay? And so this is a typical polar graph, or one example of a polar graph. And in a way, this is what we would call a form, I don't want to say linear, because it's obviously not linear, but basically anytime you have theta to the first power, let's get rid of the 6 and the pi here. Anytime you have theta to the first power, and then maybe you have like a plus 3 on it, and maybe you have a coefficient in front of it, like what we would have in like 2x minus 7. Say we put a 2 here. Anytime you have the form a coefficient theta and then plus or minus a number, you wind up with a nautilus shape or a spiral. If we go up to 200 pi, it's just going to keep spiraling and spiraling and spiraling. Okay, that is what you get when you do a theta to the first power. Okay, now what I want to show you is that you can do other interesting, neat shapes. Let's say that we didn't put a theta in at all. What if we just did r is equal to a number like 3? Okay, that would mean that the radius is 3 no matter the angle. So at an angle of 0, you would have a point right here. Okay, so you would have a point you would have a point right there if the radius is 3. Okay, also you'd have one 3 units away at a diagonal here. You'd have 3 units away at a diagonal here. You'd have a whole bunch of them that are 3 units away. You'd also have one up here at this point right here, which would be at the rectangular coordinates 0, 3. You would also have one at -3 and 0. And you would also have one at 0 and -3. And you might be thinking to yourself, is there a shape that has a radius of 3 no matter what the angle is? Well, yes, there is. So let's go ahead and put in r equals 3. Oops, that's 32. R equals 3. And look, there it is. That's the shape. It's a circle. So here's what I'm telling you. I'm telling you that when you do a polar function where you don't have a theta at all, you just have r is equal to a constant, the result is a circle that has a radius equal to what you put in. You want the circle to be larger? Okay, well, you can put in r equals 4. Or how about r is equal to 5? Look at that. The circles get larger and larger. How about a smaller one, r equals 2? It creates concentric circles. We can even do one in between. How about r is equal to 2.5? Okay, and so you can make circles that radiate out from the center when you just do r is equal to a number. Okay. All right, and then you can play around with this. Let's say you could just pick anything. How about r is equal to, we did theta squared earlier, right? How about theta squared minus, and you can throw in some trigonometric functions, cosine of theta, okay? And it'll create a weird shape. We still got the spiral here, but it did something weird with it. Instead of starting right here, it curled it back, okay? All right, well, how about just r is equal to cosine of theta? What does that do? Okay, well, that just creates a circle kind of on the side. How about r is equal to 2 cosine of theta? Oh, it looks like it gives it a circle with a larger radius. Actually, that one had a radius of 1/2. Now it's a radius of 1, and now it's a radius of 2. Okay, we can also do sine of theta, which will now put the circle on the top side of the x-axis instead of the right side of the y-axis. If we multiply this by theta, look at that weirdness. All right, we can scroll out here and look at this. This is very strange. Yeah, you can get a lot of really cool looking shapes with polar functions. And the whole reason I'm showing you this is you might be the kind of person who's interested in neat designs, and polar functions can be used to create very, very neat designs. Okay. Also, if we do cosine of theta, but let's say we did cosine of 3 theta. Oh, look at that. Check this out. All right, let's go back to cosine of 2 theta. 2 theta, look, gives us a clover. 3 theta gives us a 3-leaf flower. 4 theta, 5 theta, 6 theta. Oh, what was that? 66 theta? 7 theta, 8 theta, 9 theta, 10 theta. That's a pretty looking flower right there. So you can create neat looking shapes with polar functions. Let's change it to sine now. Okay, sine of 2 theta. Oh, we still have the 4-leaf clover, but it turned it by about 45 degrees. 3, 4, 5, 6, 7, 8, 9, 10. Once again, we have that flower again. And so you can have a lot of fun with polar functions. That's all I really wanted to show you here. Okay. All right, so that's it for the beginning, for being able to calculate the outputs of polar functions, and also being able to look at polar graphs. What I'm probably going to do on the quiz is I'm going to give you some polar graphs that you'll have to go into Desmos and type in and match them up to their polar function.